Good morning class and welcome to another lecture on sustainable energy technology. This will be a brief lecture where we will finish our discussion on hydroelectric power systems by a tutorial session with a few worked out examples that will show you how to use the understanding, the technical know-how and the formulas that we have discussed over the last 2 or 3 lectures on different types of turbines and use them effectively in solving numerical design problems. So with that, we will start today's work. So let's just state the problem as it is stated and then we will continue. So here the problem is as follows. Consider a watershed that has a head and flow rate sufficient to install a hydropower station having power P. Okay. So we have a hydropower station which has a certain amount of power, which can deliver a certain amount of power P. So let eta be the ratio of generated electric power and available mechanical power of water. Okay. This is called eta m. Sorry about that. Eta m, the mechanical efficiency. It's a ratio of the generated electric power and the available mechanical power of water. We will assume that eta m is 0.9. Okay. Also assume that wheel to nozzle radius ratio, that is capital R by small r is equals to 12. Alright, and number of nozzles n is equal to 6. So we have to calculate the optimum nozzle radius wheel radius and rotational velocity of the Pelton wheel when available head HA is equals to 10 meters and the generated power P is equals to 0.1 megawatts. Okay, so let us look at what are the main inputs. Okay, the power, that is electrical power, that is being generated is 0.1 megawatt. the available head of water is 10 meters. Remember, this is available head, so frictional head has been taken into account already. The number of nozzles N is 6. The ratio of the wheel radius, Pelton wheel radius and the nozzle radius is 12. And the mechanical efficiency is 0.9. And we have to find the actual values of the optimum nozzle radius, optimum wheel radius, and the rotational velocity omega of this Pelton wheel. So let's see how this can be done. So at optimum conditions, Pm equal to half eta m into number of nozzles N into the jet area Aj into the density of water rho W into 2G into available head to the power 3 by 2. We derived this expression before, if you remember. So the available electrical power is the mechanical efficiency into half into number of nozzles into the area of the jets issuing from that nozzle into the density of water into 2G into available head to the power 3 by 2. Right? And what is the available jet area? Which is half eta m n into pi r square, where r is your nozzle radius, density of water 2GHA to the power 3 by 2. Okay, this implies r square is 2 of the optimum power, maximum power, into eta m n pi rho w 2G HA to the power 3 by 2. Fine. Now PM is 0.1 megawatt, so 0.1 into 10 to the power 6, that is 10 to the power 5 watts. Rho W is 1000 kgs per meter cube, the density of liquid water. Number of nozzles is 6. Eta m is 0.9. HA is 10 meters and G is 9.81 meter per second square. So you can put all of these values together and you will get R square equal to 0.00429 meters, implies the nozzle radius R is 0.0655 meters. Okay, then the wheel radius capital R is basically 12 times the nozzle radius small r, because our capital R by small r is 12, so this is 0.786 meters. Okay, under optimum conditions, the rotational velocity omega is the jet velocity by twice capital R, as we discussed earlier, right? So this is equals to root over 2GHA by twice R equals to 8.91 radians per second. Okay, now this is in radians per second, so if you want to do this in RPMs, revolutions per minute, then becomes 8.91 into 60 by 2 pi revolutions per minute. Second to minute 60 and radians to revolutions divided by 2 pi. This is 85.1 RPM. So these are your three answers that you are looking for. Okay. So another, we will do another worked out example. So let's continue. So suppose we have a hydropower plant that needs to be installed in a location where average volume flow rate of water is 50 meter cube per second. So the average volume flow rate of water is 50 meter cube per second. The available head of water is 7 meters, and the efficiency of electricity generation is 0.9. We want a 50 Hertz AC output, and the generator has 6 magnetic poles. So we wish to choose the turbine that is best suited for this location, given that the ratio of generator shaft speed and turbine shaft speed is 3/2. Okay. So the idea here is we want to have a hydropower plant which is installed in a location where the volume flow rate of water is 50 meter cube per second. The available head of water is 7 meters. The efficiency of electricity generation is 0.9. And we want a 50 Hertz AC output from this generator, and the generator has 6 magnetic poles. So we want to choose the turbine that is best suited for this location, given that the ratio of the generator shaft speed and the turbine shaft speed is 3/2. So how do we go about that? So firstly, we have to figure out how much power is being delivered by this generator. Okay, so the power generation by the proposed hydropower plant is W dot equals to efficiency into density of water into G into available head into the volume flow. This is the overall efficiency. Rho G H A is the available head, and this is the volume flow rate. Okay, so this is the mass flow rate into the total potential energy available of water, and this is the overall efficiency. So overall efficiency is 0.9, density of water is 1000, G is 9.81, available head is 7, and volume flow rate is 50 meter cube per second. So this gives you If you multiply all of them together, 3.09 megawatts. Okay, so this is the expected electricity production rate for this hydropower plant. Okay, next we look into what is the RPM of the shaft itself. Okay, so we have 50 hertz AC output, fine, and number of magnetic poles is 6. So omega of the generator shaft is the 50 hertz AC output, 50 into 60 into 2 by 6. Okay, so this is the AC output rate, this is the number of magnetic poles, 60 is basically the conversion factor from radians per second into RPM for this case, and 2 is the is another formula there. Okay, so this gives you equal to, and we have discussed this conversion before, right? This gives you 1000 RPM, fine. And we also have omega turbine by omega generator as 2 by 3. Okay, omega generator by omega turbine is 3 by 2, so this is 2 by 3. This implies omega turbine equals to 2 by 3 into 1000 RPM equals to 666.67 RPM. So the angular velocity of the turbine shaft is 666.67 RPM. Okay. So the required specific speed for the turbine omega s equals to 0.262 into omega turbine into W dot to the power half, as we had discussed, into HA available head to the power minus 5. Okay, this is the expression for the specific speed that was used for selecting of the turbine. The RPM of the turbine shaft, the W dot to the power half, the power generated by this turbine, and the head available head I to the power minus 5 by 4. So this becomes 0.262 into 666.67 into 3.09 into 1000. Remember, this W dot was in kilowatts, right? So that's why this is here. The omega turbine is in RPM, and the available head is 7 meters to the power minus 5 by 4. So this gives you 852.77. So if you look at the values of specific speed for the various turbine types, this best fits the Kaplan turbine. Okay. So this is how you can use the values for the various heads, for the available head, for the omega of the turbine and the gear ratio to evaluate the specific speed, and hence select the type of turbine that best suits your needs. Okay. So that kind of gives you an overview of how you can use these formulae to look at the various types of hydropower plant, how to design different types of hydropower plants, how to select a hydropower plant, and that kind of finishes the major aspects of a hydropower plant that we have discussed so far. And in the next class, we will start a new chapter. We will discuss wind turbines. So just as hydropower plants basically uses the kinetic energy of water, wind turbine very similarly uses the kinetic energy of wind. It's a modern renewable in the sense that it really picked up in the last 10, 15, 20 years. It's a rapidly growing sector of the renewable energy technology, and that is what we will discuss in the next week's classes. Thank you.